Assalamualaikum and hello everyone. My name is AQILAH BINTI AHMAD and I am currently pursuing my medical studies. For my special study module, I have chosen pediatric cardiology as my area of interest. A pediatric cardiologist is a specialized physician who diagnoses, treat, and manage heart conditions in infants, children, and adolescents. Heart disease in children are commonly congenital, which is defect that is present at birth and usually before, which cause significant impacts on a child's growth, development, and overall health. When we talk about cardiology, it naturally connects us to the cardiovascular system, which consists of the heart, major arteries, arterioles, capillaries, venule, and veins. The major function of the system is to deliver oxygenated blood to cells and tissues, and to return venous blood to the lungs for gaseous exchange. Main organ in the cardiovascular system is the heart, which is roughly the size of human's face. Now, let's dive deeper into the anatomy of the heart. The heart lies within the mediastinum, raised on the superior surface of diaphragm and positioned left of the midline. It is anterior to the vertebral column and posterior to the sternum. Next, the border of the heart. There are four borders, which are superior, inferior, right, and left border. From the anterior view, the front surface of the heart faces the chest wall. At the top, the pulmonary trunk, superior vena cava, and ascending aorta serve as major vessels. Moving downward, the right pulmonary artery and right pulmonary veins are visible, carrying the oxygenated and oxygenated blood. Below them lies the right atrium, marked by the auricle and the right ventricle, separated by the coronary sulcus and the anterior interventricular sulcus. At the base, the inferior vena cava collects blood returning from the lower body. In contrast, the posterior view highlights the back of the heart, where the left common carotid arteries and left subclavian artery branch off the aortic arch at the top. The left pulmonary veins are prominent, transporting oxygen-rich blood from the lungs to the left atrium. Additionally, the coronary sinus is a key feature here, collecting the oxygenated blood from the heart's own muscle tissues. Dominating the posterior aspect is the left ventricle, which forms the heart's apex and is responsible for pumping oxygenated blood to the rest of the body. The heart is encased with the pericardium, a double-walled sac that protects and anchors the heart. The outer fibrous pericardium provides structural support, while the inner serous pericardium consists of the parental and visceral layer. The visceral layer, also known as the epicardium, directly covers the heart surface and houses the coronary arteries, offering an additional layers of protection. The heart itself is made up of three primary layers. The epicardium serves as the thin, protective outer layer and containing vital blood vessels. The myocardium, the thick middle layer, composed of cardiac muscle, powers the heart's contraction. Finally, the endocardium, a smooth inner layer, lines the chambers involved, minimizing friction and facilitating efficient blood flow. The heart comprises four chambers: the right atrium and right ventricle, while receiving the oxygenated blood from the body and pump it to the lung via the tricuspid valve and pulmonary valve, and the left atrium and left ventricle, which handle oxygenated blood from the lungs and pump it to the body through the mitral valve and aortic valve. Major blood vessels include the superior and inferior vena cava, which return the oxygenated blood to the right atrium, the pulmonary vein, which bring oxygen-rich blood from the lungs, and the aorta, which distribute oxygenated blood to the body. Within the ventricle, the papillary muscle and chordae tendinae stabilize the valve during contraction, preventing backflow. The trabecular carinae, reach along the ventricular walls, enhance blood flow by reducing suction. Together, the pericardium, heart layers, chambers, valve, and internal muscle features ensure the heart operates efficiently as a coordinated pump maintaining blood circulation and support the body vital functions. Moving on to the physiology of heart and cardiovascular system. Blood circulates through the body via two interconnected pathways, which are pulmonary circulation and systemic circulation, which work together to deliver oxygen and nutrients while removing waste products. In pulmonary circulation, the oxygenated blood enters the heart through the superior and inferior vena cava, filling the right atrium. It flows through the tricuspid valve into the right ventricle, and during contraction, the blood is pumped through the pulmonary valve into the pulmonary trunk, leading to the lungs via the pulmonary arteries. In the lungs, gas exchange occurs as carbon dioxide is released and oxygen is absorbed, reoxygenating the blood. While the systemic circulation begins as oxygenated blood returns to the heart through the pulmonary veins, entering the left atrium. It flows through the mitral valve into the left ventricle, which pumps it through the aortic valve into the aorta. The blood is then distributed to the body tissues via systemic arteries, where oxygen and nutrients are delivered, and carbon dioxide and waste products are collected. The oxygenated blood returns to the heart through systemic vein, completing the cycle. This continuous process ensures all body tissues are adequately supplied with oxygen and nutrients while efficiently removing waste, maintaining vital bodily function. The cardiac cycle is a continuous sequence of events that occur from the start of one heartbeat to the start of the next. It involves electrical and mechanical events that ensure the heart pumps blood effectively. So the first one is initiation. The cycle starts when an action potential is generated spontaneously in the SA node located in the right atrium. This electrical signal rapidly travels through both atria and then through the AV bundle into the ventricle. Secondly, nodal delay. There is a brief delay around 0.13 seconds as the action potential travels from the atria to the ventricle. This delay allows the atria to contract and fill the ventricle before ventricular contraction begins. The timing is systole contraction lasts about 0.3 seconds and diastole, which is relaxation, lasts about 0.5 seconds. For the mechanical phases of the cardiac cycle, phase 1, atrial contraction. The atria contract, pushing the remaining blood into the ventricle to ensure they are fully filled. For the second phase, isovolumetric contraction, the ventricle begins to contract but the AV and cerebellar valve are closed. This causes a rise in pressure without any changes in the volume of blood in the ventricles. For the third phase, rapid ejection, once the pressure in the ventricle exceeds that in the arteries, the cerebellar valve opens and blood is ejected quickly into the aorta and pulmonary arteries. For the fourth phase, reduced ejection, the ejection of blood slows down as the ventricle continues to contract, but the pressure difference between the ventricle and artery decreases. For the fifth phase is isovolumetric relaxation. After blood is ejected, the ventricle begins to relax. During this phase, all valves are closed and the pressure in the ventricle drops, but no blood enters yet. For the sixth phase, rapid filling, as the pressure in the ventricle falls below that in the atria, the AV valve opens and blood rapidly flows from the atria into the ventricle. For the last phase, which is reduced filling, the rate of ventricular filling slows down as the ventricle becomes nearly full and prepared for the next cycle. One example of biochemical process is cardiac action potential. The cardiac action potential is the electrical signal that drives heart muscle contraction. It begins with depolarization, where voltage of sodium channel open, allowing sodium to rush into the cells. This causes a rapid rise in the membrane potential, making the cells become positively charged. Next, the plateau phase occur, where calcium channel open allowing calcium to enter the cell, while some potassium channel remain open to let potassium exit. This will maintain the membrane potential at a steady level, allowing the heart muscle to sustain contraction. Finally, during repolarization, the calcium channel closes and additional potassium channel open, allowing more potassium to leave the cell. This restores the membrane potential to its resting state, ensuring the heart muscle relaxes before the next contraction. This cycle, lasting about 0.3 seconds, enables the heart to pump blood effectively. Is congenital heart defect. A defect that is present at birth. Among the several congenital defects that affect the heart is the septal defect. A septal defect is an opening in the septum that separates the interior of the heart into the left and the right side. For the first example is ventricular septal defect, which is VSD. VSD is the most common type of congenital heart defect. It is a hole in the wall of interventricular septum that separates right and left ventricle. The oxygenated blood flows directly from the left ventricle into the right ventricle, where it mixes with the oxygenated blood. The factor of VSD is caused by incomplete development of the interventricular septum. And the signs and symptoms is fatigue, shortness of breath, heart murmur, cyanosis if severe shunting occurs. For the second example is atrial septal defect, which is ASD. ASD is an abnormal opening in the atrial septum, causing the blood to flow between the left and right atria. The sign and symptom is fatigue, shortness of breath, heart murmur, and cyanosis, sounds just like the VSD symptom. The factor of ASD is in an atrial septal defect, the fatal foramen opule. The main surgical approach used to repair or close ASD or VSD is open heart surgery. Other than that, treatment options for ASD and VSD include medications, a plug or other specialized device insert through a catheter or surgery.